The grand tapestry of the cosmos continuously unfolds before our eyes, while human curiosity remains an unceasing vessel, sailing toward the light within the vast darkness. Since ancient times, looking up at the starry sky has been an intrinsic instinct. We have sought to understand those flickering points of light, weaving them into stories and even calculating their orbital trajectories. Yet, as our scientific instruments grow increasingly precise, we have discovered that beyond the known celestial bodies, a massive secret may still lie hidden. The solar system is our familiar yet enigmatic home, and its boundaries are far more expansive and complex than we once imagined. In the distant, frigid reaches of space, subtle clues from gravitational interactions are quietly pointing toward an invisible giant, a celestial body scientists refer to as Planet 9. Inheriting the legacy of Planet X from a century ago, it has become the most captivating astronomical mystery of our era. This story is not merely about the discovery of a new planet, it is a century-spanning relay of exploration, a journey into the deep history of our solar system, and yet another challenge to the limits of human knowledge. Our journey has never ceased, and this time, it points toward the furthest shadows of our neighborhood. The history of our understanding of the planets is a long one, a tale best told in the quiet of a dream. Before we begin, remember to engage with our community. Our story began with the observation of the 5 planets visible to the naked eye, all moving in an orderly fashion under the sun's gravity. It was not until the invention of the telescope in the 17th century that humanity broke through the limitations of natural vision. In 1781, the British astronomer William Herschel accidentally discovered Uranus, more than doubling the known size of the solar system. However, this new planet soon troubled astronomers. Its orbit seemed slightly off, showing minute deviations from the precise predictions of Newtonian gravitational laws. Though these discrepancies were subtle, they captured the attention of the scientific community. Astronomers began to speculate that an unknown planet might exist beyond Uranus, its gravity tugging at the planet and causing it to drift from its theoretical path. This bold hypothesis sparked an unprecedented mathematical race. 2 brilliant mathematicians, Adams of Britain and Leverrier of France, independently performed complex and arduous calculations to reverse engineer the position of this unknown planet from the orbital anomalies. After years of painstaking work, Leverrier sent his results to the Berlin Observatory in 1846. Just 1 day later, based on those precise predictions, the observatory directed its telescope toward the specified region and miraculously discovered the stranger in the dark. This planet was later named Neptune. Its discovery was a magnificent triumph for science, validating the universality of Newtonian mechanics and proving that even an invisible gravitational ghost could be captured through rigorous calculation. Yet, the joy was short-lived as new problems emerged. Although Neptune's gravity explained most of the anomalies, its own orbit appeared somewhat irregular. This triggered fresh speculation about another mysterious planet in the deep reaches of the system. At the turn of the 20th century, an American astronomer named Percival Lowell became the leading force in the search for this planet X. With a passion for the unknown, he established the Lowell Observatory in Flagstaff, Arizona, dedicating himself to the hunt. He believed a massive undiscovered object beyond Neptune was quietly disturbing its path. Lowell spent years photographing the sky, looking for faint specks of light moving against the backdrop of stars. Though he did not find the planet himself before passing away in 1916, his mathematical predictions and tireless spirit paved the way for his successors. In the late 1920s, the observatory hired a young, self-taught enthusiast named Clyde Tombaugh. His task was to continue the grueling work of comparing thousands of photographic plates using a specialized blink comparator. After long hours of meticulous labor, he finally discovered a faint moving point of light in early 1930. This was announced as Pluto, the ninth planet. At the time, it was believed that Pluto was indeed the planet X Lowell had sought, seemingly ending the decades-long search. However, Pluto's discovery did not perfectly explain the orbital irregularities. As measurements became more precise, astronomers were shocked to find that Pluto's mass was far too small to exert any measurable influence on Neptune. Its discovery was a beautiful coincidence, not the legendary Planet X. This realization sent the mystery back to its starting point. Moving into the 21st century, observation technology evolved rapidly, and our understanding of the solar system's edge underwent a revolution. Astronomers discovered a vast number of icy bodies forming the Kuiper Belt. Pluto was redefined as a member of this massive population rather than a standalone planet. In 2006, the International Astronomical Union officially removed Pluto from the list of major planets. The title of the ninth planet fell away, but this transition set the stage for a new search based on fresh evidence. The ghost of Planet X, which had briefly allowed Pluto to take the throne, was wandering the edges of the solar system once more, though its traces were now more elusive. It was no longer proposed because of Neptune's orbit, but rather through the strange behavior of a group of distant, small icy objects. These bodies seemed to be guided by an invisible hand, performing a synchronized and peculiar dance. Their orbits pointed in the same direction, as if an unknown gravitational master were in control. In the silent darkness of the outer solar system, new mysteries emerged in the 1930s and beyond as we realized Pluto was not alone. The Kuiper Belt was found to be a massive ring filled with hundreds of millions of icy objects. As telescope technology improved, we discovered larger bodies like Eris and Makemake, which challenged our very definitions of what a planet is. Yet, the real puzzle appeared when astronomers noticed that a specific group of objects in the deep Kuiper Belt possessed highly eccentric orbits with perihelions, their closest points to the Sun, clustered in the same region of the sky. Their orbital planes were also tilted in the same direction. The probability of such a configuration occurring by chance is extremely low. This level of coordination suggested a powerful gravitational source was acting like an invisible vacuum cleaner in a dusty room. Against this backdrop, two astronomers from the California Institute of Technology, Konstantin Batygin and Mike Brown, began a deep dive into the data. Through complex computer simulations, they considered every known gravitational influence, and concluded that only a massive planet, 5 to 10 times the weight of Earth, could explain this behavior. They called it Planet 9. Their research, published in 2016, caused a sensation because it was built on rigorous mathematical and statistical evidence. Unlike Lowell's old hypothesis, this was based on the collective behavior of a population of objects acting as gravitational probes. They described Planet 9 as a shepherd dog, herding these distant bodies into specific orbits. This hypothesis was later supported by independent research teams using different data sets. The hunt has now moved from theoretical calculations to a global search using the world's most advanced telescopes. This search is far more difficult than the one for Neptune. Planet 9 is so far away that the sunlight it reflects is incredibly faint, obeying the physical law that light intensity diminishes sharply with distance. It is likely hundreds of times dimmer than the faintest objects we can currently see. Furthermore, because its orbital period spans tens of thousands of years, its movement across the sky is painstakingly slow, making it easy to mistake for a background star. Astronomers must scan vast regions of the sky, comparing images taken months apart to find a single moving dot. This monumental task has invited a new force into the fold: citizen science. Projects like Backyard Worlds, Planet 9 allow the public to help astronomers by scanning processed images for anomalies. Human eyes are still uniquely skilled at recognizing patterns that algorithms might miss. This democratization of science has accelerated the search and led to the discovery of many new brown dwarfs and icy objects. Every new piece of data feeds back into the theoretical models of Bodigen and Brown, creating a dynamic loop of correction and refinement. Even if Planet 9 is never found, the search itself is invaluable. Each empty scan narrows down the possibilities and expands our knowledge of the furthest reaches of our home. The hypothesis of Planet 9 remains a brilliant star on the edge of the solar system, but in the spirit of scientific skepticism, it must continue to withstand the challenge of alternative explanations and rigorous testing. Following the proposal of the Planet 9 theory, many astronomers did not simply accept it without question. Instead, they began exploring alternative possibilities, seeking non-planetary explanations for the orbital anomalies observed in those distant Kuiper Belt objects. The emergence and debate of these alternatives have not weakened the weight of the Planet 9 hypothesis, rather, they highlight the rigor and diversity of scientific exploration from a different perspective, forming a fascinating chapter in this cosmic detective story. The most direct skepticism concerns whether these strange orbital clusters might simply be a statistical coincidence. In scientific research, we often find patterns that appear regular, but upon deeper analysis, these patterns may be nothing more than illusions created by randomness in small data sets. Regarding these distant objects, the number we can currently observe is still just a tiny drop in the ocean compared to the theoretical total population of the Kuiper Belt. Astronomers worry that what we perceive as clustering might be the result of observational bias. For instance, are our telescopes and survey methods more likely to find objects with specific orbital parameters? If such a bias exists, the pattern we see is not a true physical phenomenon, but a mirage produced by our own limitations. To verify this, scientists have conducted extensive simulations, creating virtual Kuiper belts with millions of randomly distributed objects and subjecting them to current observational constraints to see if they could reproduce similar clusters. These studies have yielded varying conclusions. Some suggest that bias explains part of the clustering but not all of it, while others maintain that even after accounting for every known bias, the alignment of these distant orbits remains a real physical reality that cannot be dismissed as a statistical fluke. This ongoing debate over statistics serves as a vital reminder that in any scientific discovery, we must remain highly vigilant about data reliability and the limits of our analytical methods. Beyond statistical illusions, a second compelling alternative is the massive debris disk hypothesis. This theory suggests that the orbital anomalies are not caused by a single giant planet, but by a vast, diffuse collection of matter hidden at the edge of the solar system. This matter could consist of millions of undiscovered icy small bodies whose collective mass is sufficient to influence the orbits of the Kuiper Belt. Because this mass is spread out, no single object can be detected as a planet, yet their cumulative gravitational pull cannot be ignored. This hypothesis is attractive because it does not require a new planet, only the assumption that the solar system's edge is more densely populated than we thought. However, proving this also faces immense challenges. First, it must explain how this diffuse matter is distributed in such a specific way to cause such tight clustering, which is difficult to reconcile with current models of solar system formation. Second, if such a massive disk existed, it should have left gravitational traces on the trajectories of distant interstellar probes like Voyager 1 and 2, Yet no such evidence has been found. Nevertheless, this hypothesis offers a fresh perspective, suggesting the boundaries of our solar system may be far more complex, harboring forms of matter we have yet to uncover. The third and perhaps most cinematic alternative is the primordial black hole theory. This bold idea proposes that a tiny black hole, formed by density fluctuations in the very early universe shortly after the Big Bang, might be hiding in the far reaches of our system. Such a black hole would have the mass of a planet but would be extremely small and emit no light, making it nearly impossible for traditional telescopes to see. If such an object exists at the edge of the solar system, its gravity could perfectly explain the strange behavior of the Kuiper Belt objects. While it sounds like science fiction, it is not without a basis in physics. Primordial black holes are a major topic in theoretical research and could even help solve the mystery of dark matter. If the purported ninth planet is proven to be a black hole, it would be one of the greatest physical discoveries of the century, reshaping our understanding of the solar system and deeply impacting particle physics and cosmology. To verify this, we would need to look for other clues, such as gravitational lensing effects as it passes through interstellar dust or faint radiation from its interaction with matter. These clues remain purely theoretical for now, with no conclusive evidence yet. The existence of these alternatives reflects the core of the scientific spirit, critical thinking toward existing hypotheses. This forces scientists not only to search for a planet but to constantly refine their theories and rule out other possibilities. Every failed attempt to prove an alternative strengthens the credibility of the Planet 9 hypothesis. Conversely, if we find that the anomalies are indeed explained by one of these alternatives, it would be an equally thrilling discovery, revealing deeper secrets of our solar system. This quest also makes us reconsider the nature of scientific discovery. It is not just about finding something new, but about using a mystery to explore the unknown and challenge our collective knowledge. Whether it is a ninth planet, a statistical illusion, or a miniature black hole, every possibility points toward an untouched chapter in the history of solar system evolution. The search for Planet 9 is more than a scientific detective game, it is the ultimate test of the human boundary of exploration. The end game of this chase, whether we find the planet or prove its absence, will have a lasting impact on our perception of the universe. The vanguard of this final battle will be the next generation of astronomical equipment. These new scientific tools will conduct a systematic search of the distant reaches with unprecedented precision and breadth. One of the most anticipated tools is the Vera Rubin Observatory, currently under construction in Chile. Equipped with a massive 8.4-meter telescope, its unique capability lies in its ability to survey the entire southern sky with incredible speed and depth. Each exposure can cover an area as large as 40 full moons, allowing it to remap the same region every few days. This power will enable it to easily catch a slow-moving, faint object like Planet 9 if it exists. The Rubin Observatory was designed to find things that change or move, making it the perfect tool for this hunt. Within the next decade, it is highly likely to be the place where the discovery is finally made. The sheer volume of data it produces daily will require entirely new processing techniques, ensuring that even the most subtle signal has nowhere to hide. Alongside ground-based efforts, the James Webb Space Telescope provides a new perspective in the infrared spectrum. This is crucial for finding cold, distant objects that reflect very little visible light but emit faint heat absorbed from the sun or left over from their formation. While its field of view is too small for a wide-scale survey, it can be used for high-precision observations of specific regions identified by models or ground-based surveys to confirm a discovery. Its participation is like bringing the most advanced forensic tools to a crime scene, allowing for the precise analysis of the smallest clues. However, we must also calmly consider what it would mean if Planet 9 is proven not to exist. Such a result would still hold immense scientific value, forcing us to re-examine the Kuiper Belt anomalies and take the alternatives seriously. If a statistical illusion is the cause, it means our understanding of the outer solar system is deeply flawed, requiring a revolution in how we analyze data. If a diffuse mass disk is confirmed, it reveals a new chapter of evolution where massive amounts of material were cast out to the edges in ways we do not yet understand. Regardless of the outcome, it will challenge our theories on how planets form and what the true boundary of our solar system looks like. The ultimate significance of the search for Planet 9 transcends the finding of a new world. It is a grand narrative of how humanity understands the cosmos and uses the scientific method to solve the unknown. It shows that even in an age of information, the universe still holds countless mysteries. From professional astronomers to citizen scientists, everyone can contribute. When we look up at the stars, we know that beyond the familiar points of light, a great secret may still be hidden, the ultimate case of the solar system's ninth planet. This journey, regardless of the destination, will be a chapter in human history worth remembering. That is all for our discussion today. May you have pleasant dreams and a wonderful day ahead. We will see you in the next episode.